With the third law now under our belt, I think it's useful to point out that it actually is consistent with some of the definitions for statistical entropy that we've seen in earlier lessons. So for example, the Gibbs expression for statistical entropy looks something like this, where we take a summation over all the states of the probability log probability to calculate that. And we've shown also that this is a way of also getting to the Boltzmann expression, which is written in terms of the number of microstates that the system may have. So how would this be consistent with the third law? Well, the third law implies that S goes to 0 as temperature goes to 0K. But what does that really mean? Well, in the case of these statistical things, what we're basically saying is that as temperature goes to 0, there's very little motion, and in fact the system collapses into one state. So we might say that there's one state that has a probability of 1, and all of the others, and it has energy of 0, and all of the others, so Pj equals 0 for j not equal to that lowest state. So how does that jive with this? Well, if we have one state that has probability of 1, that means I have only one microstate. All right, that's the only state that can be achieved by this system. And if I have only one microstate, log of W is going to be 0. So in this case, the Boltzmann definition certainly gives us a value of 0 when this is the case. If I just have one probability that's 1, that means I have one value of Pj that's 1, but log of 1 is equal to 0. All of the other Pj's are equal to 0, so all of these will be 0, and I'll have to worry about what is the limit of the log as that goes to 0, but since it's multiplying by 0, all of that will be 0. So in effect, both of these statistical definitions of entropy indicate entropy going to 0 when I have this sort of situation involved in these states. So they're very consistent with this notion of the third law. All right, so we can basically assume now that for a given temperature, this is going to go toward this integral that we've described in the previous video of Cp over T dt, where this little t is just a variable that we use as a placeholder for the temperature so that we can have the temperature up here in the integration limits that refers to the entropy. So these are quantities now, because these depend upon a heat capacity. These are quantities that can ideally be determined by a calorimeter. So this gives us a ready-made way that we can experimentally determine the entropies that we might get for an absolute entropy that we might get for a particular substance, because we have a way now of calculating something like this using information that we get directly from an experiment. Now, we also use extensively the partition function for finding these absolute entropies. And let me talk a little bit about what that means. So I have a system partition function that's equal to the molecular partition function over n factorial. But I also know that this molecular partition function can be written as a series of contributions. And in particular, those contributions include the translational contribution, the vibrational contribution, the rotational contribution, and the electronic contribution. And all of these things are combining to create a molecular partition function, which now I'm going to raise the n, but this is really just the same as 1 over n factorial z trans raised to the n power times z vibe raised to the n power times z rot raised to the n power times z electric raised to the n power. Now, we'll probably discuss this a little bit more in upcoming lessons, but in reality, we see that most of the contribution comes from these two factors. And the reason I say that is if we're talking about temperatures that are in a normal scale like 300 Kelvin, there's typically only one electronic state. So in that case, the electronic partition function is particularly simple. It's either equal to 1, or if that lowest electronic state has a particular degeneracy, it could be equal to the degeneracy of that 0th electronic state. So that's about as far as it goes for most electronic problems. there are obviously exotic alternatives. Z-Vibe is an interesting case because at normal temperatures, a lot of the vibrations, in fact, have too high a vibrational temperature for many of the excited states, the higher states than the lowest one, to contribute to this partition function in vibration. It can contribute a little bit, but most of the contribution we'll find comes from the translation and, oops, I didn't mean to mark the electronic, the translation and the rotation is where we're going to get most of that. So when we see values that are given for absolute entropy, and so these are the things that we'll see tabulated in thermodynamic tables. This typically is labeled S0 to indicate the absolute entropy, and it's typically reported for a standard temperature. So I'll say reported at 298.15 Kelvin, for example. All right, so when we're looking at these things in the table, they have basically gone through the evaluation of S of t as we described it in the previous video, the one about absolute entropy. So this is something that is calculated or measured, or sometimes both. What's interesting is that we find through the use of partition functions or through the use of this particular function for S of t, we find that there's actually really good agreement between what is measured experimentally and what is calculated basically just from a few basic features of a given molecule. Now let's take a look at some actual absolute entropy values and see if we can understand what these things mean. So let's first focus on this table on the left. What I'm showing you are a series of molecules in the gas phase, starting with argon, which is obviously a noble gas, carbon monoxide, and then a couple of triatomics. So these are pretty simple molecules, but I chose them because they're all gases essentially at room temperature. So since all of these are going to be measured at a temperature of 298 Kelvin, I wanted these all to be gases. Now the absolute entropies, we can learn a little something about how these are structured as well. So for example, for argon, essentially the only contribution that we're going to get to this absolute entropy is a translational contribution. So that's the only piece, this piece up here, that's going to give us any value here. And we find that for a lot of noble gases, their absolute entropy is right about this value. The only way that they change is through their mass. And remember that the translational partition function was dependent upon the mass raised to the 3/2 power, and then you take the logarithm of that. So in this case, this is a fairly typical value for argon. So now when we go to carbon monoxide, what has happened here? Well, we now have a diatomic molecule, so there are both vibrations and rotations that can contribute. Carbon monoxide has a little bit different mass than argon, but it's actually lighter. Argon has a mass of 40 grams per mole, whereas carbon monoxide is 28. So it's a little bit, it's about 3/4 the mass of argon. So that would cause the absolute entropy to decrease. It increases though because primarily of the rotational contributions. All right, there's probably a little bit of contribution from vibration, but it's not contributing a lot there. What about when we go to No2 and So2? Well, these are both a little bit, they're a little bit more massive than carbon monoxide or argon. No2 is 46, So2 is 64, so we're now really getting somewhat more massive. And that explains in part why we have higher values for their absolute entropy. But we're also adding vibrational degrees of freedom. And remember that for a linear molecule, there are only 2 rotational degrees of freedom. But for these triatomics, there's 3 rotational degrees of freedom. So there's going to be a bigger contribution from rotation. They're more massive. So all of these things help to explain the increase in absolute entropy when we go from carbon monoxide up to nitrogen dioxide and sulfur dioxide. All right, let's take a look over at the other table. Now in this, what I want to do is draw a contrast between liquid and gas states. So I'm showing you 2 substances that can exist as both liquid and gas at temperatures comparable to 298. So bromine actually is a liquid at room temperature, but it easily is vaporized into a gas. Now we can see that the result of going from liquid phase to gas phase adds about 100 joules per mole Kelvin to the entropy content of the bromine. So gas is quite a bit more, I'll say S vapor is quite a bit more entropy filled than the entropy of a liquid. We see the same in the case of water, and in fact the difference is even greater than it is for bromine. Now, one of the things that I should note here is that the entropy of liquid water is somewhat lower than the entropy for liquid bromine. Why is this? Well, we all know that liquid water, in fact, has special hydrogen bonding intermolecular forces that hold it together. This actually gives liquid water a greater sense of order to it. That is to say, there's less randomness involved in it. And we know intuitively from other aspects of entropy that entropy is going to be greater the randomness or the greater the disorder in the system. So this is telling us basically that liquid water is a more ordered liquid than liquid bromine. For vaporous water, however, there is quite a it's not as entropy filled as vaporous bromine, but it's still got a lot more entropy than liquid water. So again, we see this large increase as we go from the liquid phase to the gas phase in this case. Now, these are trends that one sees throughout a lot of different kinds of molecules. I'll note that if one were to look at the entropy content of the various noble gases, you would see that as the mass increases, the entropy content increases, as I mentioned. The same is going to be true of the hydrogen halides. Again, they're all very similar compounds, but as we have a heavier and heavier halide associated with it, the absolute entropy of those hydrogen halides is going to increase. So this is a little bit of a crash course on practical values of entropy, but I hope now you can look at those tables with a new understanding of where some of those figures come from and what they mean.